So in today's video, we are going to be talking extensively about the concept of mutually inclusive events. We would also talk about how we can use the concept of Venn diagram to diagrammatically represent two mutually inclusive events, and also define the mathematics that we can use to work on two mutually exclusive events. You're talking about the addition rule and the multiplication rule, and then we solve one or two questions to help us understand the basis of this type of event. So let's move to the definition of mutually inclusive events. In simple terms, two events are said to be mutually inclusive if they can occur simultaneously, that is, they can occur at the same time. Let's take an example of two events. Let's say the first event is you listening to music and the second event is you jogging. There's a chance that you can be listening to music and be jogging at the same time. Both events can actually coexist, that is, both events can occur simultaneously. The occurrence of one of the events does not affect the other. So the events of you jogging and you listening to music are both mutually inclusive events. Another example can be the event of you listening to music and you eating. So there's a chance that you can be eating, and there's also a chance that you can also be listening to music at the same time. Both events can actually occur simultaneously. So definitely, eating and listening to music are actually examples of mutually inclusive events. So let's try to pick a more mathematical example, and I am going to be assuming the example of the sample space of rolling a fair die just once. The sample space of rolling a fair die just once is actually equals to 1, 2, 3, 4, 5, 6. So let's assume we want to pick an event. Let's say the event of an even number. So the event of an even number from the sample space of rolling a fair die is going to be equals to 2, 4, and 6. So let's assume you want to take another event from this experiment, and we say the event of a prime number. So the prime number right here, we have 2, we have 3, and we have 5. So we have 3 prime numbers, we have 3 even numbers. As we can see, there is actually an intersection between these two sets. That is, there is actually a common value or a common element between these two sets, and that value is equals to 2. That is, the value 2 showed up in the first event and the value 2 also showed up in the second event. So that simply implies that the first event and the second event, that is the event of even numbers and the event of prime numbers, are actually mutually inclusive events because they have an intersection, they have a common element, and it simply implies that they can actually coexist. So let's try to learn how to use the Venn diagram to diagrammatically represent mutually inclusive events. And basically, this concept actually goes with how we worked with mutually exclusive events. The universal set is represented with the rectangle, which also represents the sample space, and the circles represent the given set, which in this case of ours represents each of the events. So that simply means if we have 2 events, then we are going to be having 2 circles and 1 rectangle, and if we have 3 events, we are going to be having 3 circles and 1 rectangle. So let's assume the example of just 2 events. How do we use the Venn diagram to diagrammatically represent them? This circle represents event A and that circle represents event B. So in the Venn diagram world, or using the set theory, this is the Venn diagram that defines two mutually inclusive events. As we can see from this Venn diagram, there is an intersection between the two sets. That is, there is a region between the two sets where they can coexist, where they can occur at the same time. So the mathematics that define the mutually inclusive event is given as we have probability of A union B is equals to P into brackets A plus P into brackets B minus P into brackets A intersection B. Or we can say probability of A or B is equals to probability of A plus probability of B minus probability of A and B, where probability of A and B is actually equals to probability of A times probability of B. So these are the addition and multiplication rule for mutually inclusive events. So let us move into our worksheets to solve one or two questions that can help us understand the basis of mutually inclusive events. So these are the 2 questions we are going to be using to explain the basic concept of mutually inclusive events. So we have question 1 and we have question 2. So let us start with the first question. So the first question says, in a group of 25 boys, 20 play ice hockey and 17 play baseball. They all play at least one of the games. So the question now says, what is the probability that a boy chosen at random from the class plays ice hockey but not baseball? We need to pay attention to the details, to the wordings being used in this question. So the question says they all play at least one of the games, which simply implies that there is a chance that you can play both hockey and baseball at the same time. So that means that the two events are actually mutually inclusive. So it says that in a group of 25 boys, so that means we have a total number of students, or the total number of boys, to be equal to 25. So that represents the universal set, and the number of students that plays ice hockey, we have 20 of them. So we have to extract out the details. So the universal set, so we can say mu, which is the total number of students, is actually equals to 25 of them. And the number of students, or the number of boys rather, that plays ice hockey, we have that to be equals to 20. So that means the number of H. So this represents the number of students that plays ice hockey. We have that to be equals to 20. And it also says that 17 of them actually plays baseball. So that means the number of students that plays baseball is actually going to be equals to 17. So the question went on to say that they all at least play at least one of the games. So what is the probability that a boy chosen at random from the class plays ice hockey but not baseball? So one of the best ways to actually solve this question is to use the concept of Venn diagram. So meaning we are going to use the Venn diagram to diagrammatically represent this question so that we can see the necessary regions we are working with and do the mathematics. So let's try to use the Venn diagram right here. So I'm going to start with this circle. So I'm going to say, so this circle right here represents ice hockey. So we have ice hockey right here. So it was mentioned in the question that they all play at least one of the games. So that means that a student can actually play ice hockey and baseball. So let's try to duplicate this circle. So we have another circle right here. So this is going to intersect right here. So let's make this red. All right. So this right here represents baseball. So we can just call this baseball. So the black marker represents those number of students that plays ice hockey, and the red marker represents those number of students that actually plays baseball. So we need to have a universal set, and that is where the rectangle comes inside. So we have to draw the rectangle. So let's just draw it right here, and then we'll drag it over here. All right, and this is the Venn diagram that represents our question. So right here we write our universal set mu to actually be equals to 25. So as we can see from this Venn diagram, we have some regions that we have to work with. Take for example this region right here that I'm shading with the blue marker actually represents the region of the intersection between both ice hockey and baseball. So this is the region that defines the point where a student can play ice hockey and baseball. So let's take that away. The whole of the red marker, that is everything right here, represents the number of students that actually play baseball. So this right here represents the number of students that plays baseball. These represent the number of students that plays ice hockey. Everyone right here actually plays ice hockey. Now this region right here, as you can see, I'm shading this region. So this region that I'm shading, as you can see, actually represents those that actually plays ice hockey only. That is those that played ice hockey but they did not play baseball. And this region right here represents those that played baseball only but they did not play ice hockey. So that is just the Venn diagram of this question, and the sum of all of those regions must actually equals to the universal set. So to make things easier for us, I'm going to give each of the regions letter. So let's call this letter A, which is the region of intersection. I call this letter B, which is region of ice hockey only. I call this region C, which is the region of baseball only. And I call the outer region, this region right here, which is region of not baseball nor ice hockey. So region D is actually the region of students that did not play either of ice hockey or baseball. So the sum of all the regions, that is A plus B plus C plus D, must actually equals to the universal set, which is equals to 25. But we have to pay attention to something. The question says that they all play at least one of the games. So if the question says they all play at least one of the games, so it's never possible for a student not to play either of the games. So in this question of ours, this value is going to be 0 because it is never possible for a student not to play either of ice hockey or baseball. So the first step is for us to get the number of students that plays both ice hockey and baseball, and as you can see, it was not stated in the question. So what do we have to do? We can use the letter X to represent that region. So X is the number of students that plays both ice hockey and baseball. So the next step is for us to fill in the necessary details. So how many students plays ice hockey? We have a total of 20 students. So the black circle right here represents the total number of students that plays ice hockey, but we have some region taken with X. So if the whole of ice hockey is actually equals to 20, and we have this region right here, which is X, representing both ice hockey and baseball, so this region right here is going to be equals to 20 minus X. All right, so let's move to baseball. The number of students that plays baseball, we have that to be equals to 17, and we've already taken out X out of this. So if this is X, then definitely here is going to be equals to 17 minus X. And like I mentioned earlier, it is never possible for a student not to play at least one of the games, because it was stated in the question that they all play at least one of the games. So that means the value outside the circles must be equals to 0. So now that we have values for each of the region, we can use this simple rule right here to sum all regions, that is equating to the universal set. So that simply implies that 20 minus X plus 17 minus X plus 0 is actually equals to 25. So let's do the math. So we have a 20 plus 17 minus X plus X minus X is actually equals to 25. So 20 plus 17 actually gives us 37. Minus X plus X goes to 0, and we have minus X is equals to 25. And when we do the algebra, we have our X to be equals to 37 minus 25. So 37 minus 25 actually gives us 12. So the number of students that actually plays ice hockey and baseball are actually 12 of them. But that is not the question that is being asked. The question being asked is, what is the probability that a boy chosen at random from the class plays ice hockey but not baseball? So we need to know the number of students that plays ice hockey but not baseball. And what is the region of ice hockey only, or ice hockey but not baseball? And that is this region right here, the region of 20 minus X. So we can just stick this a bit to the left. So number of ice hockey but not baseball, so we can just throw the bracket in, is actually equals to 20 minus X, and that is going to be equals to 20 minus 12, which gives us 8. So 8 students in the total of 25 students actually plays ice hockey but not baseball. So the probability of ice hockey but not baseball is actually going to be equals to the number of students that plays ice hockey but not baseball, and that is going to be equals to 8 divided by the total number of students, which is equals to 25. And when we convert this to decimal, we have our answer to be equals to 0.32, which is 32%. So there's a 32% chance that a student picked at random will play ice hockey but not baseball. So let's move to the second question. So the second question says that there are 30 children in a class and they all have at least one cat or dog. 14 children have a cat and 19 children have a dog. What is the probability that a child chosen at random from the class has both a cat and a dog? Pay attention to the question. It says that in a class and they all have at least one cat or dog. So that simply implies that there's a chance that a student can have both a cat and a dog. So meaning the event of having a cat and the event of having a dog are actually mutually inclusive events, meaning they can occur at the same time. So let's use the Venn diagram to solve this question again. So let's take this up a bit. So the universal set is actually equals to 30. So we have our mu to be equals to 30. And we were also told that the number of students that have cats is actually equals to 14. So the number of cats is actually equals to 14. And the number of children that have dogs is actually equals to 19. So just like we did earlier, we're going to be using the Venn diagram to represent this. So let's draw our circle. So we have this circle right here. And then we copy it. And then we paste it to have the same circle. So we intersect them. So we are intersecting them because the question mentioned that it is possible for a student to have both dog and cat. And then we draw the universal set, which is the rectangle. Our universal set right here is actually going to be equals to 30. So that means mu is equals to 30. So we can call those cats and we can call this dog. So we need the number of students that actually owns both cat and a dog, and as we can see, it was not mentioned in the question. So that means we're going to be using letter X to represent that. So the total number of students that owns a cat is actually equals to 14. So if the total circle for black is equals to 14, so that means this region right here is going to be equals to 14 minus X. And for dog, we have a total of 19 students owning a dog, so that means this region right here is going to be equals to 19 minus X. Since it was mentioned that at least one children must own either a cat or a dog, it simply implies that this is going to be 0. So that being said, let's try to sum all regions to equal it to the universal set, and that is going to be equals to 14 minus X plus 17 minus X plus 0 is actually equals to 30. So we have 14 plus 17 minus X plus X minus X is equals to 30. So 14 plus 17 is actually equals to 31 minus X plus X minus X is actually equals to 30. So we have 31 minus X is equals to 30. So we have X is equals to 31 minus 30, and that is going to be equals to 1. So the number of children that actually own both a cat and a dog is actually equals to 1. So that means just one child actually own a cat and a dog. So the main question is, what is the probability that a child chosen at random from the class has both a cat and a dog? And the probability that a child owns a cat and a dog is going to be equals to the probability that we have a cat and a dog. That's going to be equals to the number of children that owns both cat and a dog divided by the total number of students. And as you can see, we have just one student that owns a cat and a dog, and we have a total of 30 students. So when we convert this to decimal, 1 divided by 30, that gives us 0.033. So there is a 3.33 approximately percent chance that if a child is chosen at random, that child is going to own both a cat and a dog. If you enjoyed this video and you learned something new, I would really appreciate if you can give this video a thumbs up and also subscribe to this YouTube channel. Thanks for making it to the end of this video, and we see you in the next one. Bye for now.